Welcome back to Introduction to IP Multicast. I'm Tim McConaughey. I'm delivering this breakout. This is part 3 of the breakout. In this part of the breakout, we're going to cover any source multicast. If you haven't seen part 1 and part 2 yet, I would suggest that you go back, take a look, watch those first, because with any source multicast, we're going to be building on the multicast fundamentals we've already used and learned. Without further ado, let's just jump right into it. Now, up until now, when we've been talking about multicast fundamentals, we've been assuming that the receiver knows who the source is and knows where they want to receive the multicast traffic. But a lot of times that's not the case. For multiple reasons, the receiver might not be able to signal for a particular source, or it may not know a particular source as part of the multicast application. And that's where any source multicast comes in. Any source multicast means spinning the wheel of sources. We use any source multicast in cases where the receiver just doesn't know where the sources are that are sending to a particular multicast group. And of course, it's the only option when we're using older versions of IGMP on the receiver. In IGMP version 1 and version 2, we had no field to request a specific source. That wasn't added until version 3. So because of that, it's really the only option for earlier versions. It is still supported in version 3, but it's not required. Multicast routers have to learn where the sources are in order to deliver that multicast traffic. That's fundamentally how the multicast works. We need to dig that canal, build that river towards the source in order to deliver multicast to the receivers. But what do we do when we don't know where that source is? Well, someone made a movie about it. It's called Kittens in the Mist, the Any Source Multicast story. There's a few players we need to pay attention to, some leading ladies and men, if you will. First of all, we need the first hop router. We'll need our last hop router twins, and introducing for the first time will be our rendezvous point. And to talk about how a rendezvous point works, we should talk about something with which we're all intimately familiar these days. Of course, I'm talking about food delivery services. Let's talk about how any source multicast works in terms of multicast food delivery. So when a restaurant wants to be able to find customers, it will send its menu to the food delivery service. So in this case, we're talking about something like Grubhub or DoorDash, Uber Eats, one of those type of services that will list a restaurant's menu and what food is available for delivery for customers. So the source sends its multicast traffic to a particular group, and it hits that first hop router first. So the first hop router could be seen as, say, the front of the house. We could call it the front of the house router. And we could say that the multicast server is sending the menu to the front of the house router. The front of the house router is going to want to register its menu with our RP hub, if you will. So the first hop router will take this multicast traffic that it's receiving. It will establish what's called a PIM tunnel or unicast tunnel through the network towards the rendezvous point that's been configured. And it will send the rendezvous point some of that multicast traffic in unicast tunneling. And when the rendezvous point receives that traffic, it will register that traffic. Now, this could be analogous to, again, the front of the house router sending the menu to our RP hub, and our RP hub will be saving that menu and providing it to customers that are going to come looking for particular food. Now, if there's no customers already waiting for that food, then the rendezvous point sends what's called a PIM stop or a register stop message back to the FHR saying, okay, I'm aware that you have multicasts. I would like you to stop right now because I don't have anyone to deliver it. Again, multicast is about scaling and optimizing our traffic flows. So in this case, we have lovely young lady. She's got her glasses or ponytail of her MacBook. I think we have a pretty good idea what she may be looking for. And she wants some really delicious avocado toast, which is something I actually enjoy myself. So what comes next is from the receiver, and that's what's called the star comma G PIM join. Well, the receiver actually is going to send an IGMP report, as we've established, and from the multicast router will come the star comma G PIM join. So think about it this way. We have our lady sitting in front of her laptop. She's going to press the button, go to RP Hub. She's going to signal that she wants avocado toast. And so that's our IGMP report for a specific multicast group. She's saying, I want avocado toast. And when that hits the LHR is going to convert that into a star comma G PIM join. So at this point, we know what multicast group we're interested in, but we have no idea what the source is. We have no idea who's sending or who's selling avocado toast. And as LHRB is the designated multicast router for the segment, the DR, the multicast router, there's a couple different terms here, it will send that PIM join to the rendezvous point. Now, why doesn't it send it towards the source as we've seen before? And of course, the reason is because at this point, we actually don't know who the source is. So we can't perform our RPF check and we can't send it, forward that PIM join out of the interface towards the source. But we will do an RPF check and we will forward that PIM join towards the rendezvous point because we know where the rendezvous point is. So when we're talking about star comma G PIM joins, we're talking about kind of this setup here. That RPF check is checked against the rendezvous point, not against the source, because we don't know who it is yet. And that's an important part of the any source multicast setup, and this is where a lot of people get confused. Now, when the rendezvous point receives that PIM join and adds that interface to the outgoing interface list towards LHRB, the RP looks at its multicast table and says, has anyone registered as a source for this group? In this case, we know that our FHR has sent that multicast traffic and registered itself and saying, I have a source that's sending to this multicast group. And so now what the rendezvous point will do is send its own PIM join towards that FHR to be added to the outgoing interface list. And so having received that PIM join, the FHR adds that interface to its outgoing interface list, and multicast traffic now begins to flow. It flows down towards the rendezvous point because that's where the PIM join came from. But first, we've now placed the order. The next thing to happen is when the rendezvous point receives that multicast traffic, it's going to deliver it down its own outgoing interface list towards LHRB. And something important happens when LHRB receives that multicast traffic. It's going to receive that multicast traffic and see the source address in the packet. And that tells the LHR that, hey, here's a source. You should go ahead and deliver this traffic to the receiver. And so the LHR, again, delivers traffic down its own outgoing interface list. But while it does that, it also sends a new PIM join. And this is called the S comma G, or the source group pair, the source group PIM join. Now we know who the source is, and we can do what we saw earlier, where we decide what is the best interface towards that source. That's the interface I'll forward the PIM join. And that PIM join gets forwarded up to the FHR. And then just like we saw before, the FHR, having received the PIM join, will send multicast traffic down its outgoing interface list, and every router in the way will do this as well. And so now, eventually, the receiver is actually receiving 2 multicast feeds, but it only needs 1. So one more important thing has to happen, and that is what's called the prune. The star comma G prune is being sent from the LHR to the RP. So the LHR sends a specific message, a special message called a PIM prune, towards the rendezvous point. And it says, I've already got a better path for this multicast traffic. I don't need to be added to your outgoing interface list anymore. Please remove me from the outgoing interface list. And so the RP removes that interface from its oil, the outgoing interface list. And if it has no other interfaces to deliver traffic, the RP prunes itself. It sends its own PIM prune. And this is the kind of the end state, which is the best path through the network from the source to the receiver. Now, what happens if this young lady has a roommate? The roommate smells the avocado toast and decides it's delicious. Now, does the roommate have to go all the way to RP Hub in order to order this food? Well, no. We now know what restaurant is delivering this food. So instead, the client just sends an IGMP report, and we're going to basically trench in the multicast traffic, which is to say, wherever the closest outgoing interface list is, we're going to simply add the interface towards this receiver and deliver the traffic that way. And that allows us, without having to rebuild and redo this entire process, it allows us to add receivers. Now, what if we have multiple sources? Well, here's where any source multicast tends to get a little weird. So any source is also every source. What that means is that any source in the network that is sending to a particular multicast group, if it's registered with that rendezvous point, the rendezvous point is aware of both sources, which is to say both feeds, and something weird will happen when a receiver asks for that multicast traffic. So when this happens, when LHRB sends a PIM join, a star comma G join, towards the RP for a particular multicast group from the receiver, we didn't ask for a specific source. And so the RP, not knowing what source we're interested in, will instead send its own PIM join for every single source that is sending to that group and just rely on the receiver to figure it out, basically. So multiple feeds will end up getting received and delivered down the outgoing interface list towards the receiver. And then it's up to the receiver's multicast application to figure out what to do with that. Now, obviously, if both sources are sending completely wildly different feeds, say one is playing a movie and the other is playing, I don't know, say music, this is going to be extremely ugly to the receiver. This is not a normal thing. What you do see is in financials especially, what you'll see is what's called an A side and a B side flow. So your A side server, say the purple server on the left, or the server with the purple line on the left, will send the same traffic into the network, but from a different location than, say, the B side, which would be, say, our blue arrow. And even though they're both sending the same flows, they're located in different places. And this is kind of a redundancy disaster recovery type of setup, where if one flow disappears, the other flow still is being sent. And so the receiver is still receiving the application traffic. And then the receiver's application will do something like discard one of the feeds or something like that. There'll be some thing inside the application that does something to either blend or discard the multicast feeds. Okay, so we'll talk about one more thing, and it's kind of a corner case. You don't see it a lot in the wild. It's called bidirectional PIM, and this is our many-to-many multicast solution. So think about a network where, say, we're doing, I don't know, we're playing a video game or something, and everybody is a source, and everybody is a receiver. And we need everybody to listen to everybody. So multicast requires a lot of state tracking. Anytime a source sends, and anytime a flow is built, you see there's a lot of multicast route maintenance that has to happen to keep those flows going to the correct places, to check on whether those flows are still happening, if prunes are coming in, if receivers are leaving. There's a lot of maintenance that happens to multicast. So there's a lot of state tracking. And when you add more sources and more receivers, that just goes up exponentially. So what bidirectional PIM attempts to do is to solve that state tracking problem by simply discarding or getting rid of tracking altogether of state, of sources specifically, not of state, sorry, but of sources. So we don't do source tracking. Instead, what we do is place the rendezvous point in the data plane. So this is now because we're not tracking sources anymore, we're not doing RPF checks either. So because we're not doing reverse path forwarding checks, we have kind of a weird problem where we can get loops everywhere. And so we solve this by making the rendezvous point itself part of the forwarding plane, if you will, for the multicast feeds. So everything's built towards the rendezvous point. So this is very similar to spanning tree with a spanning tree root bridge. And this is how we get around the scaling limitations of tracking all these multicast sources, is we simply stop tracking the sources and stop doing reverse path forwarding checks. Instead, we do kind of a spanning tree solution where, again, we build towards the rendezvous point, and each segment has a designated forwarder to forward multicast traffic. That was an awful lot to take in, so hang in there, baby. Let's talk about rendezvous point redundancy, and specifically how we do redundancy and we do dynamic RP discovery. So rendezvous points are extremely important. I think we can all agree. Because of that, we need rendezvous point redundancy, and we also, just for scaling purposes, we need a way to dynamically select or elect a rendezvous point for a network or a segment. So these are the problems we want to solve. How do all the multicast routers agree on who is the RP? And they need to agree, because in order to rendezvous, we need to send all our PIM joins to the same place, and the sources need to register to the same place. So how do we discover that? How do we decide who is the rendezvous point? The other problem is what happens when that rendezvous point fails. If we fail with any source multicast, for flows that are not already built, we're just done. Those flows will never get built because they have no way to find their sources. So how do we provide redundancy for that rendezvous point? Those are the two problems we're trying to solve. There's a couple of ways to solve it. One is kind of the older legacy way, and that's using a solution called AutoRP. Now, AutoRP is like the Cisco proprietary solution, the first one that came out. AutoRP uses what's called a mapping agent to listen for candidate RPs to advertise their willingness to serve the function of a rendezvous point. So it's a configuration you add to a router, and that router simply then listens on dedicated multicast groups to learn, hey, who wants to be a multicast RP? So there's two groups, and these groups are flooded. They're used in dense mode multicast, which is to say that we're simply going to flood this everywhere. We're not paying any attention to RPF. We're not paying attention to sources and any of that information, right? If you're tuned into this group, it's just flooded out to every segment. Now, 224.0.1.39 is the one that the candidate RPs will flood to, saying, I am willing to be a rendezvous point. And the reason it has to flood that out is because it doesn't know where the mapping agent is. Because if you configure the mapping agent on the router, you might as well have just configured the rendezvous point. So again, we have kind of a chicken and egg problem here where we need to discover our mapping agent so that we can learn who the actual RP is. But in order to do that, we need to flood it out. The other group is used by the mapping agent itself to send to all the routers, RP or otherwise, saying, okay, I've talked to the candidate RPs, I've made a decision, everyone use this rendezvous point. So this is tuned into by every router. 224.0.1.40 is tuned into by every router. 224.0.1.39 is only tuned into by mapping agents that are listening for that advertisement. This is the old way of doing it. Now these two groups, they run in dense mode, like I said. They're flooded out, and that's kind of inefficient. Again, there's a reason we moved away from dense mode. The other thing is that this particular solution, AutoRP, is the reason why we have PIM sparse dense mode. So if you remember in, I can't remember if it was part 1 or part 2, but I covered PIM and the different modes of PIM. And PIM sparse dense mode, I said, was kind of a deprecated, not used solution that was only really ever used for one purpose. This was the purpose. So instead of configuring PIM sparse mode on all of your interfaces, if you wanted to use AutoRP, you had to configure PIM sparse dense mode, just so you could carry these groups and do AutoRP. Now, Cisco came out with a command later that basically made that pointless, which is called IPPIM AutoRP Listener. And that is a config that tells the router, hey, you need to listen to this group. And so it wasn't required anymore to do PIM sparse dense mode. Now this is kind of a dirty way to do it. This was the first way we did it, and it works. But there's a better way now. And that better way is using something called BSR or Bootstrap Router. Now, the Bootstrap Router is actually very similar to how the mapping agent works. And again, the BSR solution is the standard, the IETF standard. Now, Bootstrap Router is, again, a config we add to a router, and we say you're a Bootstrap Router. And that Bootstrap Router will listen to RP advertisements from candidate RPs. These RPs will, again, send messages saying, I want to be the RP. And then it's the Bootstrap Router's job to listen to that and then elect one. Now, in this case, because it's an IETF standard, we're actually using the PIM messaging protocol that already is on for multicast to accomplish this. We're not flooding dense mode multicast groups. We're simply adding it to a PIM hello, saying, hi, here's my PIM hello. By the way, I'm a Bootstrap router, so tell your friends. And eventually the whole network area will learn who is the Bootstrap router. And this allows us to do something that we couldn't do with AutoRP, which is to unicast the candidate RP's willingness to be the RP to the Bootstrap router, because the candidate RP now knows where to send the packet. So it will unicast that rather than flood it out. And that's a huge bonus over AutoRP. Now, when the BSR actually chooses who's going to serve as the rendezvous point, it's going to use that same native PIM messaging to advertise the selected RP. Again, so it doesn't have to flood out to everyone, say, use this RP. Instead, it just uses the PIM hello saying, this is actually the RP we're going to use. So much better, much more elegant solution. Now, there's a caveat to how multicast RP selection works, and I devote a whole slide to it because it's something that kind of flies in the face of how we do most everything else at Cisco. Now, I dynamically learned RP. If you learn an RP via BSR or AutoRP, that actually takes precedence over a statically configured RP. Normally, it's the other way around. If I statically configure something, that's the way it is, right? And we simply ignore dynamic advertisements. This is backwards. If I learn it via BSR or AutoRP, even if I have an RP configured, if it's a different RP, I'm going to use that one instead. I'm going to use the one that I learned dynamically. To look at our multicast demo topology, I've activated the BSR topology, so I can just show you what Bootstrap Router looks like. In this topology, the Bootstrap Router will be MCAST B. So this guy right here is going to be our Bootstrap Router. This guy is actually going to be our rendezvous point. So MCAST A is going to be our candidate RP advertising to MCAST B its willingness to be the RP. Then only after MCAST B has sent PIM hello messages that eventually make it to MCAST A, saying that it's the Bootstrap router. So first MCAST B says, I'm the Bootstrap router, use me to elect your rendezvous point. When MCAST A learns that, and it's configured to be a candidate RP on the loopback 0 interface, MCAST A will unicast to MCAST B its willingness to be the RP. And the result of that will be that MCAST B selects it as the RP and advertises it all around to everyone. Let's look at the CLI there. Now here we are at MCAST A. Remember that MCAST A is going to be our rendezvous point. If we do show IPPIM BSR router, we can see that the Bootstrap router is 4.4.4.4, which is our MCAST B's loopback. and it's been up for a while, and then it sees that the candidate RP is its own loopback 0, 3.3.3.3, and then you get some information about the hold time and advertisement interval. The result, if you look at show IP PIM RP mapping, will show you for which groups certain RPs are performing the function. Now you can see that this system is a candidate RP, and that for the groups 224000/4, or the entire multicast range, the elected RP is 3.3.3.3. That question mark after it has to do with DNS, name resolution. For some reason, they decided that name resolution should be part of this. And you'll notice that the info source is 4.4.4.4, which is the bootstrap router. So again, the bootstrap router made the election and then informed that router, hey, you told me you were the candidate RP. Well, I'm pleased to inform you, you're the actual RP. And you can see there's some priority in uptime and some other timers there. So that's how the whole bootstrap router process works. The AutoRP process is slightly different, but basically the same. Again, the BSR is much like a mapping agent. There's just a lot more of dense group flooding involved in that process. Let's skip over and we'll add a receiver and start showing you what a star comma G looks like, a star comma G PIM join sent to the RP, and then we'll send some traffic to that group and we'll see what the switchover to the shortest path or the source river looks like. Let's take a look at how the whole ASM thing works. Okay, here we have a topology where we have no receiver requesting multicast. We have no sender sending multicast. It's kind of a pristine topology. We have a rendezvous point configured with BSR. We have all of our routers in path, and we have no multicast routing state being tracked right now. So if we look at the mroute table of our LHRB, which is the designated multicast router for the receiver, we can see only one entry, and that entry, that 224.0.140, is kind of an always-on entry to support AutoRP on Cisco routers. So even if you're not using AutoRP, the solution, you usually will see this group kind of tuned in anytime you have a Cisco router that is using multicast. So we can kind of ignore that because we're not using it, but just that's why it's there. You can see no other state being tracked, no star comma G for requesting of a group, and no S comma G or no source sending to the group right now. So LHRB doesn't know about anything multicast related, and we can bounce over to our RP. You can see that MCAST A also has no multicast state. There's no sources registered, and there's no receivers requesting multicast. MCAST B isn't really part of this yet, but we just want to look and see that it's the same. We have no sources or receivers. And then the FHR, or the first hop router, is not receiving any multicast traffic and has not received any star comma G PIM join or anything like that to receive traffic. So again, kind of pristine here, but I wanted to take a look at all of the mroute tables just to show that nothing is happening right now. So what we'll do is we'll take our receiver, we'll try to join a group, and we'll see what that looks like, and then we'll send to the same multicast group from a sender or a source, and we'll see what happens basically with the network. So let's do that now. So just sending the IGMP report should have triggered the last hop router to receive that report and change it into a PIM join. So if we look at the mroute table now, we can see a star comma G PIM join, and we can see that the RP is 3.3.3.3, which is our MCAST A router. We can also see that we have an outgoing interface. Our outgoing interface list is gig02, which leads towards the layer 2 access switch for the segment, which is the interface on which it received the IGMP report. The incoming interface is going to be the interface on which it forwarded the PIM join. And again, we did the RPF check against the rendezvous point, not against the source, because we don't know who the source is. And that's it. It forwarded the PIM join on, and so we should be able to go to the rendezvous point now and see whether or not it has the star comma G PIM join. So let's look at the routing table there. We can see that it did receive the star comma G PIM join. Notice that the incoming interface list says null. That means that the rendezvous point has not received any PIM register message from a source that is sending to that multicast group. So there's nowhere to forward a PIM join from the rendezvous point's perspective. It did receive the star comma G PIM join, and the outgoing interface list is based on where that PIM join came in. So that interface gig03 is down to LHRB, but again, we have no traffic flowing yet. There's no source sending. And we can verify that by looking at our first hop router and look at the mroute table. And again, we have no S comma G or source group pair. We have nothing sending to a group. Notice also, importantly, that the first hop router doesn't have any PIM joins. There's no star comma G PIM join in the mroute table because the RP is not going to forward. Well, first of all, it can't. It doesn't know where the source is, right? So the RP can't forward a PIM join to this FHR because it has no idea that there's a source connected. It hasn't received the PIM register. So I'll start some traffic and we will see everything very quickly. And so it'll be kind of a post-mortem. We'll actually have to go through and look at the mroute table and see what happened. We won't be able to catch it in real time. It's too fast. But let's take a look at that. So we'll set some traffic just by pinging the multicast group. So 1.2.3. And we'll repeat it, say, I don't know, 100 times, just so we can keep the traffic flowing. And let's just see if it's receiving the traffic. Yes, you can see that the FHR is receiving a source group pair. This is the ping that's coming in from that server. So 10.4.17.7 is that server. You see it's sending the group 239.1.2.3. And you can see also, look, there's a flag that says registering. So it's actually registering that traffic with the RP right now. Well, it's probably already happened, but if we take a look, see, you can see that went away. It's not saying registering anymore. It now is basically registered. So if we go to MCAST A, we should see that that's been registered. We see that the S comma G from the server is there. And notice that the star comma G entry, star.239.1.2.3 is still there. It's still in the mroute table, but it's not really being used anymore. Now take a look at the mroute table for this RP. We can see something very important has already happened that we missed. So the star comma G, 239.1.2.3, it's there. Notice that its incoming interface still says null. And that's because we don't need it. Basically, it's because we don't need it anymore. It's been cut over already. We kind of missed this process. So when the traffic came in to the RP and was registered, the traffic from 10.4.17.7, when that came in was registered, it automatically started sending that down the outgoing interface list towards the receiver. But look at this. The outgoing interface list now shows null, even though we still have an incoming interface list. And if we look at the counters, we won't see them incrementing anymore for this, by the way. The reason is the outgoing interface list is null because the last hop router has already derived the correct path, the better path, and sent its PIM join and then sent the PIM prune to the rendezvous point. It happens very quickly, and so it's kind of hard to catch. But we can verify that by going to the router that we know is the better path, which is MCAST B, and we can look at the routing table there. And if you do the show IPM route here, you can see that our S comma G entry from the source is here on this router. And we have both an incoming interface list, so that's the interface towards the source, and we have an outgoing interface list, that's the interface towards LHRB. And if we go to LHRB, we should, I believe, see two entries. So let me log in, back into this box. we should, I think, see two entries. Yes. So we see the star comma G, which is no good anymore. We see an S comma G for the source group pair from the source. And we see that the incoming interface list is gig01, which is towards MCAST B now. And the outgoing interface, of course, never changed. That was towards the receiver. So this is now already on the shortest path river, if you will, of the source river. At this point, we're done, and the receiver is receiving multicast. So there's not much else to look at here. Make sure you join me in part 4, where we'll cover Anycast RP, source-specific multicast, and IPv6 multicast, and wrap this thing up. Thanks for watching.